So first, to kind of start the conversation, started with my favorite quote here. I use this a lot if you've seen it in my presentations. With the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to a reduced quality of life and possibly to negative health effects. And this comes from the ICC, the International Code Council, their G2 2010 guidelines for acoustics. I know there's a lot of acousticians here, so this is nothing new for y'all, but for any architects, contractors, any other folks here, code, the SDC and ISC requirements in the code, they're minimums, right? And typically, as acousticians for market rate apartments and especially condominiums and things like that, we try to design above those code minimums. And so keep that in mind kind of as we're going through this conversation about shear walls and talking about the SDC ratings for them. And there's a lot of other kinds of projects, schools, hospitals, right, government buildings, all of these kinds of things where we have different, SDC targets that we're going for. Sometimes they're higher than the SDC 50 code minimum for multifamilies. Sometimes they're lower, just kind of depending on what we're dealing with. But just something to kind of set some context for us. And for some additional information, right, these are recommended ratings from this ICC guideline document, recommended ratings for multifamily. This is all around residential multifamily construction. So SDC and IC 50 are the code minimums. Sort of the acceptable performance level is SDC and IC 55. I think a lot of acousticians typically use that for like market rate apartments. Might vary from person to person, but that's what I typically see. And then preferred performance STC IIC 60. You'll see that a lot recommended for condominiums and things. So kind of keep those numbers in mind, especially really SDC since we're talking about shear walls here. So what are shear walls, right? Not to just assume that everybody here knows what we're talking about when we say shear walls. So we're talking about all the examples I have here today are wood stud walls, typically 2x4 wood stud walls. But you can have shear panels and things and steel construction as well. So the shear panels are there to just resist the racking motion of that wall, right? And so they're typically, you see them in load-bearing walls. They're there for that structure to resist the whole racking motion of the building structure. So you'll see them all over. They're even more prominent in seismic areas like here in Oregon, where PAC is, where I am, because obviously you have more stuff that might happen with that building in an earthquake event. And so you need more shear strength to resist that motion. And since it's to resist that racking motion, the shear panels, usually plywood or OSB, need to be attached directly to the studs and attached very securely to provide that shear strength. But that, of course, presents challenges acoustically, because typically in acoustics, the way we get our performance is we isolate the gypsum board, right, and all the surface layers, at least on one side of the wall, we isolate them from the structure. But in shear walls, we don't have that opportunity um, because the shear panels need to be attached directly to the structure. In a single shear, where we only have a shear panel on one side, maybe we don't have as many issues. But double shear walls, where we need a shear panel on both sides, or two shear panels, like in this double stud on the right, those present a lot more challenges, like you see here, right? So here's test data for these to start us off. So a single 2x4 wood stud wall with just shear panels on either side. Now I know there's no gypsum board on this, so this isn't sort of a final wall, right? But to show, that's an STC 36. So nowhere near the code minimum of 50 or sort of those acceptable or preferred ratings of 55 and 60, right? And even with a double stud wall, right? Double stud walls are very typical for sound isolation between, residential units, because they give a lot of flexibility in terms of mounting things, and they can provide good sound isolation, right? They're common go-to there. And but if you need shear panels, um, they can dramatically reduce the performance of that wall. So you see an SDC 43 here. And of course, on these, there is sometimes the option to move those shear panels outward, rather than having them in the middle, which really creates the biggest issue. But moving them outwards can also create other issues for, running plumbing and wires through those and things like that. It can affect some of the other building trades. So there are some reasons to put them on the inside. So kind of understand why the shear panels maybe create more of an issue, just real briefly, we basically through a wall, we have two transmission paths for sound. We have a structural path, which would be your surface layers, right? As the air waves, the sound waves hit them, right? Those air pressure fluctuations. It'll make that surface vibrate, and those vibrations will get transmitted through the structure that it's connected to, and then transmitted to the other side, and that excites the air on the other side of the wall. That's one path that we have. And we apply sound isolation like resilient channels or sound isolation clips, or we do two separate studs, right? We're interrupting or we're sort of breaking that structural transmission path. But we have another transmission path too that we need to be concerned with. And that's really what kind of comes to play in some of these double shear wall configurations, like that double stud, right? And that's this air cavity path, right? So again, the sound waves are instant upon the wall. They make this panel vibrate, right? And that panel makes the air inside that cavity vibrate, and it transmits through, makes the panel on the other side vibrate, and then radiates sound out. And so really that air inside the cavity sort of acts like a spring. And if you remember like summer camp, those big blob things, right, that they would have at the swim areas, you would jump off of it and like somebody could be on the other end of it, you'd jump off on it and the air would push the person up and they go flying in the air, shoot off, right? So we're using that air as a spring, right, to transfer the energy of the impact on one side to the other side and push the person off. That's what's happening here with this, right? So we have this one panel moving, the energy is being transmitted through the air and making the other side move. And the closer we squish those two panels together, sort of the more transmission we can get through there. It's more complicated than that, as a lot of the folks I see here know, but that's the basic gist of this. So when we have sort of a, think about, okay, well, we've got a shear wall. We have our shear layers that have to be attached to the structure. How do we get some isolation in here? Well, let's just add isolation on top of the shear panels. That improves the wall. If we remember, this base wall was an SDC 36, right? We've got a 47 now, but we're still not to the code minimum. And part of that is because we've created this little air cavity and we've got this air spring in there, right? That's transmitting energy from one side to the other. And so we can add insulation to that cavity to basically sort of damp or resist that motion of the sound waves within that cavity. And we can get performance gains. And so here we have an STC 53. So now we've brought this wall back up to above the code minimum. We've still got our double shear panels, and it's a fairly straightforward wall, right? Single layer of chip on each side, rivet clips for sound isolation. Pretty straightforward, not a super expensive wall, doesn't take up a ton of space, right? So that's the basic gist. Now I'm just going to go through and I'll show some data because there's some interesting stuff that kind of happens. And we'll talk through the data for both a single stud and a double stud wall. So just again, as a reference, as we kind of go through these, right, code minimums are 50, acceptable, maybe like market rate apartments, 55, preferred 60. So here's some double studs just to kind of show the range of these and kind of how we can work our way. So, we start with the basic wall, STC 43. That wall, if you remove those two shear panels, and I'll show the data later, that's an STC 56 or thereabouts, right? So we see a big reduction in performance by adding those shear panels. If we just add mass, see at the top right, doesn't really get us a whole lot. Add resilient channel on one side also doesn't get us a whole lot because we just haven't changed that air stiffness coupling enough to really get the performance we need. Going to the rivet clip, getting a bigger airspace, getting more isolation gets us to that code minimum of STC 50. So we'll kind of go and walk through these. So as a baseline here, just for reference purposes, right, I've given sort of a typical wall design. So here's a 2x4 wood stud wall, RC Deluxe, single layer of gyp on each side. And this one having to test at an STC 50. There's a lot of times you'll test this and it's below a 50. I would not count this wall as a 50, but that's the data that I had to pull here so I could give you TL data. So just give that caveat because I know some people will be like, oh, don't show that wall with an STC 50. Sorry. So here's this as our baseline. We see a pretty typical curve, little dip at 80 hertz, right? And then we see the coincidence dip around 2500 hertz. So now what happens if we do the shear wall, right? So here's the 2x4 wood stud wall with the shear panels, plywood shear panels on each side. Now again, we don't have gypsum board here. This isn't a fire rated wall. This isn't what you would actually use as your final demising wall. But just as a baseline to walk through this data, here's what we have. And we see a huge degradation in the transmission loss values from, like 160 hertz all the way on up. Interestingly, low frequencies, we actually see better performance. I'm comparing walls from two different labs, which I know I'll rant about is not a great thing to do. But I didn't have another good baseline to use for that base wall. So, take the low frequency data with a grain of salt, but there might be something going on there. But it's interesting to see that for that shear wall, we see sort of just this flat line at around 20 dB for our TL from 63 to 200 hertz, and then it kind of creeps up, right? But across the entire frequency range, the wall's not doing very well. So what happens as we start to add gypsum board to this? So if we add gypsum board on one side, we add mass, we see, as we would expect from adding mass to the wall, we see an increase in the TL across the entire frequency range. Helpful, but still doesn't get us anywhere where we need to be, right? Our target of STC 50. So here's what happens when we add clips and the gypsum board. And you can see that the green line being our base wall, right, our RC wall, and the gray line here being this wall with the clips, that our TL values are fairly close to the base wall, and at the coincidence dip and above, they're even higher. But we still have this kind of dip at like 400 and 500 hertz that I think controls the STC rating. So for the most part, our TL values are matching sort of our base wall, but we're still limited in this one frequency range. We add the insulation, then we improve all of that. And so now we have a wall that actually, outperforms that base wall across the entire frequency range. And of course, adding additional gypsum board layers to this can, raise that rating further, get you more into that mid-level or maybe even that preferred grade. And unfortunately, this is an older data series. I don't have additional tests with additional gypsum board in here. But you can probably fairly easily figure out what would happen by adding additional mass to this wall. So for comparison to maybe a more typical demising wall, something I saw a lot here in Portland on the apartment projects I worked on, here's a 2-1 wall, right? 2 layers of gyp direct attached to the studs, 1 layer on RC Deluxe. And you can see that the shear wall configuration, even with a single layer of gyp, matches the TLs pretty much across the entire frequency range, except for at the coincidence dip where the rubber isolator in the Rizik clip and also the presence of the shear panels sort of takes out that coincidence dip. So we can get a wall that kind of meets our typical performance, what we might expect from an RC wall. And this comes up quite a bit. We've had a number of projects just recently. I had an architect call a few weeks back, and they had a apartment project. Their corridor walls were going to be single stud with resilient channel, probably that exact wall shown there on the bottom. But at some point during construction, the structural engineer, for one reason or another, had updated the structural design and gone from, I think, a single-sided shear panel to double shear for all of those corridor walls. At the time they made the change, or the change was caught, they'd already framed those walls as single stud walls, and the project was already far enough along where they couldn't change to staggered studs or a double stud or something else to try and get them where they needed to be. So they were scrambling, trying to figure out a solution. So here's a solution that can kind of get you there where you need to be. And especially maybe more so for corridor walls where you've got doors in them and your overall composite STC is somewhat limited anyways. So single stud walls, there's the data there. And all of this data that you're seeing here is in our assembly selector in our databases. So you can log in, see the full test reports, get all the TL data that I have here. So now let's go to double stud walls. So for double stud, we'll do the same thing, just kind of walk through. As our baseline, our old handy dandy reference, National Research Council of Canada. Here's double stud wall, SDC 56. Again, I'm going to compare tests from different labs. I apologize, but I didn't have a baseline from the same shear wall test series. So here's this. I know this is a reference also a lot of you use. So here's this data, and we'll kind of compare to this as we walk through. So here's what we get when we have the two shear panels inside in that sort of interstitial space. And we can see, as you might expect, significant degradation in the TL values across most of the frequency range. We see some interesting sort of dips and peaks based on resonances and things like that, I would say. But we're nowhere near where we need to be at SDC 43. So let's look at, adding mass. Again, we see an increase across the entire frequency range, 3 points, which is about what we would expect from mass law, right? And of course, we're still not anywhere where we need to be. We could keep adding mass, but even another layer on the other side, I don't have data for it, but odds are it would be somewhere around SDC 49. So still probably not going to get us to our code minimum of 50, and certainly not sort of a TL curve that we'd like to see. So then what happens if we try to add isolation? So we add resilient channel to one side. So we gain another 3 points by adding the resilient channel. And you can see that the TL values from like 250 hertz on up basically match that NRC wall. They're higher mini frequencies. But we have this big dip from like 80 to, well, really from 200 hertz down. And that's because of that smaller air cavity between the two shear layers, right? So, and we're at an SDC 49, so we're still not at the code minimum. So if we add clips, we increase our airspace, we increase our isolation. And here we can see that we got to an SDC 50. We're basically matching or exceeding the TL of the RC wall pretty much across the entire frequency range. And the wall with the clips only has a single layer of jip on each side. So we've saved money from the material and the labor costs of that second layer of jip. We've also gotten the code. But, SDC 50 code minimum, not necessarily our desired rating. So if we add another layer, here we actually get 4 points for the addition. We see increases across the spectrum, and we're getting in more into that sort of mid-level range where we want to be. I don't have a test, I don't think, with a fourth layer total, a second layer on the clips. But, we would probably gain a few points from that. So we'd be maybe in the SDC 57 range and kind of where we'd like to be. But you can see, by adding those shear panels in here, it requires extra gypsum board, right? And the isolation clips to get us back to kind of where we were with the double stud wall, because we've created this tiny little airspace that creates much better coupling, that little air spring, right? That helps transmit sound from one side to the other. So it creates some issues, but we do have ways that we can address it. As I said before, you can move those shear panels out to the outside a lot of times. Structurally, maybe that works, maybe it doesn't, I don't know. If that's always the case. We've gone through a project where a structural engineer evaluated it and said, yeah, they could move it out. But it does create issues for other trades, right? In this case, if the shear panels are on the inside, it's easy to get in, run electrical wires, run plumbing and things like that. But if you have those shear panels in there, scheduling trades, getting all of those stuff into the stud bays can be problematic. So there may be some other reasons for construction schedules, constructability to do it this way. The last thing I want to touch on, so here, the interesting thing with this wall, I wanted to present this. This is the actual TL data from the test report. Again, all the test reports are in our database. You can see here that, this wall had very few deficiencies. It's totally limited at 125 hertz, right? So we only had 11 deficiencies total. 8 of those were at 125 hertz. So this is an interesting one because I know that there's, in the acoustics community at ASTM and everything, there's this whole conversation going on, right, about the 8 dB rule. and eliminating that. And for those that aren't part of that, any architects or contractors, anybody else joining us, the 8 dB rule is a part of how we calculate the STC rating. I've got a webinar online. You can go look at how that's all calculated and stuff. But part of the stipulation within the ASTM standard for how you calculate an STC rating is that the deficiency, the amount that the blue line is below that gray, can exceed 8 dB at any one frequency. And a lot of times in walls, like you see here, that becomes the limiting factor. The other stipulation is that the total deficiencies at all the different frequency bands can exceed 32. So here we only have a total of 11. So we're well below the sum of deficiencies limit, but we're limited by that 8 dB. And so in this discussion of eliminating the 8 dB rule, this wall would have a very different STC rating. Whether or not that's a good thing, I'm not going to weigh in on right here. But this is an interesting sort of case to look at for that 8 dB rule discussion, I think. And this is the kind of thing that comes up quite a bit. So the last thing I want to touch on, and we'll then just open it up to discussion. This is a little bit quicker one here today, is fire ratings, right? So at PAC, we put a big emphasis on fire ratings, making sure we're testing and providing designs that work acoustically, but also work for other things, structural and fire life safety. So from a fire life safety, from a UL fire rated assembly design standpoint, how do these shear panels kind of factor in? So you typically, if you go look at a UL fire rated assembly like U305, for instance, is a typical one for 2x4 wood stud walls, you won't necessarily see wood shear panels called out explicitly within that. There is a general provision, which are some just general guidelines, general provisions that UL has for sort of how you can tweak things, add things, and help sort of how to interpret the UL designs. One of those in there for walls specifically is around wood structural panels. And these are the provisions taken straight from it, right? So the addition of wood structural panels in fire rated gypsum board wall assemblies is permitted. So that's kind of how we can get them in there. Wood structural panels 4 foot wide, minimum of 7/16 inches thick, right? There's some specifications for what that thing needs to be. You can apply them horizontally or vertically. You got to stagger vertical joints. And then this is the one that really comes in. So the wood structural panels are permitted to be applied either as a base layer directly to the wall framing and under the gypsum board, which is typically what we would see, right, for shear panels, or in between gypsum board layers or over the top of the completed gypsum board layers. And you might see, plywood panels in between gypsum board layers or something like that. If you've got something where you need to mount a whole lot of stuff to the walls and you're going to be mounting it in different places, or there's going to be a lot of like fancy decorative wood trim that needs to be mounted to the walls or something. We'll see that a lot on like custom single family residences, where you're putting plywood layers in or things. So that's kind of how we get it in there. When wood structural panels are added to the wall assemblies that include furring channels, there should be no more than 2 layers, either gypsum board or wood structural panels, attached to the furring channel. So our interpretation of that is if the wood is attached, the wood shear panel is attached to the studs, you could still have 2 gypsum board layers attached to the clips and hat channel. So just something to be aware of. This is where it comes from. If questions come up on a project, you have this as a reference to point to be like, hey, this is kind of where this comes from. This is how this works. And with that, that's what I have for today. So here's contact info. And if you want to contact us, we do have online CEU courses for any architects that are here. And now we'll go ahead and open it up to questions. In the chat, it says, how do you test these walls with both layers of plywood on the inside of the studs? So the way we've built these, I actually wasn't there at the lab when we built these. Elzo was, and I think he's here. But I think in the lab they either built them and then tilted them up into place, which is probably what you would do on a job site, In the lab, they may have actually built one in the opening, applied wood to it, and then pre-built the other one and then tilted it up. I don't know. Elzo, I'm sure you've got some additional things. You were there at the lab to say how they built that particular one. I see you already said that, Steve, that they're sheeted before. Elzo says I'm right. Okay, cool. So what brand, type, thickness of insulation do you normally specify at the Rizik cavity? So brand doesn't really matter. It's typical just fiberglass bat, and it's usually R8, which I think is like 2 or 2.5 inches. So it is compressed slightly because the air cavity formed by the Rizik clips and hat channel is 1 5/8 inches. So I think R8 is about 2 inches. So it's compressed, 3/8 of an inch, but it's bad insulation. So that's not enough compression to create stiffness in the fiberglass that's going to actually transmit energy or anything like that.
We have a question from. Oh, I'm sorry. Go ahead, Mike. Go ahead.
I was just going to say, I don't think we've done any testing with other things like mineral fiber or something like that in that small air cavity. Typically, my take is that mineral fiber, based on the data I've seen from both NRC and Ben Schaefer at Pabco, that mineral fiber versus fiberglass really doesn't make that much difference, if any. In this small cavity, maybe it would, and maybe we'll go test that someday. So I see Eric Maury has a detailed question. Yeah,
can you hear me?
Are you there, Eric? Yeah, I can hear you.
Yes. Okay. This is a continuation of the online discussion you and I and Val have been having for a couple of weeks. But with the trapped air, so a couple of tests that you didn't show there that are in the California Green Book, the Office of Noise Control Handbook of STC ratings, whatever it's called, is they have the first wall you showed, which is the 2 1-hour walls in series with each other with a layer of jip on the outside and a layer of shear on the inside. They have a couple of tests that show a second layer on each of the outside layers, still with the trapped airspace, and it jacks it up to like STC 55, which has always sort of blown my mind. So one question, or 2.5 questions. So one question is, of the diagrams you were showing before, you got up to one that had 5 total layers, but you didn't have one that had 6. And I was wondering if that exists to kind of compare to the stuff that's in the California book. Yeah, so the STC 43 is your 4-layer wall.
Right, that's our 4-layer, and then let me click through here. So there's
and then you've got the 5-layer one, yeah.
Right, which is the 46. And we didn't go to a 6-layer wall or sort of an additional layer of gypsum board on that side. And I don't think, and like I put you in contact with Ben Schaefer, who had more data from this test series because they were sort of the original sponsors of it, and I don't think that he had that additional one. So I mean, like the California Green Book is very old data, and
yes,
I know that in many instances where people have gone back and tried to recreate some of the older data, they haven't been able to do it, right? So I wish that we had that other test, and maybe it's something that Ben and I can go back and redo that additional one. I mean, the fact, like looking at the TL data and looking at the sort of the sequence of these, like the 43 to 46 for adding that second layer on one side, like that makes sense, right? That sort of follows mass law, what we would expect. So to have that 46 then go to a 55 just seems very unreasonable to me. And
yeah, I 100% agree with that. And it just seemed like some goofy test, but I have actually tested the wall in the field and gotten good results of it. Results from it. Got like an NIC 53 or 54 or something like that. I don't understand the physics, but so the second half of the question is, sort of a difference between what you've shown here, which is having shear panels on the inside, and having a separate one where you have the two firewalls in series, where I would assume, and so an internal discussion here is with the test that I guess Owens Corning did back in the Stone Age, they didn't necessarily have that inside cavity caulked. So there would be some leakage, a little bit of leakage, which would allow the airspace to be a little bit bigger. And with a shear panel, you don't need to caulk it. If it's a firewall, maybe you do have to caulk it. I think the test that you and that you had sent over, I think the top plates and the bottom plates and the side plates were all caulked to make it a nice trapped 1-inch airspace. I don't have an answer to this. I'm not necessarily expecting you to have an answer to this. I'm just, as more testing is done, how well sealed that airspace is a variable we're looking at in trying to understand these crazy 6-layer walls that in the Green Book do well, and in the limited testing we have done on them test well. So sort of throwing it out there for some anecdotal what have yous, and maybe something to keep an eye on, because it turns out that the original STC 43 tests that you have there, they're in the Green Book, they did actually go in and caulk the best they could the gypsum board that was on the inside to really trap that air, whereas the other ones maybe they
didn't.
And that's the
Yeah.
end of my monologue.
Well, thanks. I appreciate the input and the field data that sort of corresponds to what's in the Green Book is really interesting. Also, you were there at North Orbit when they built these. Do you know how they applied the plywood shear panels? Like, was there any sealant applied to those? Obviously, on the outside, the gypsum board was sealed and taped, and obviously the outside, it's typically these assemblies are sealed to the test opening with mastic or duct seal or something like that, right? But was there any sort of special sealing for that test done to the plywood, like where they butted up against each other or anything like that?
No, there was not.
Okay.
If we go back and look at the Owens Corning research from the 60s and 70s that I was a part of decades and decades ago, the result of that research is doing all kinds of internal sealing does absolutely nothing for noise. That you want to do your sealing at the outermost layers of your assembly, creating the biggest possible cavity. Putting acoustical caulking under the stud or top plates, bottom plates, a waste of money and a waste of time. So basically do all the sealing on the outside. Interior shear panels are there for the sole purpose of structure, and caulking, sealing, or gluing is not an advantage. So we've always, in PAC's methodology, used Owens Corning fiberglass for no other reason than I got a lot of my knowledge from those people for free. And the sealing is always on the most outer layers in any assembly.
Yeah. Okay, so so there weren't any special provisions made for sealing those inner shear layers there. I've definitely seen variations in performance, like results, especially at low frequencies, due to differences in boundary conditions, right, with how the assembly is mounted in the test opening. And maybe those don't show up as much in the typical data, but maybe in this wall, because these tend to be 8-point limited at low frequencies, maybe those boundary conditions are having a more pronounced effect in these walls, and that's why we're seeing, especially in these sort of smaller laboratory openings, variations in results. All of this stuff gets tricky, especially at low frequencies, and there's big
Right.
lab to lab variations too. So I don't know. I mean, I think that North Orbit's low frequency data is more reliable, they have one of the bigger receiving chambers. So they have better confidence intervals at lower frequencies. But there's obviously there's a lot of variation at low frequencies. So even if I went back and redid the test, I don't know that it would shed too much light on it. It would probably just
Right.
raise more questions than answer them, but at least it would be additional data to kind of to look through and maybe give us some clues.
We have a question from Steve Pettyjohn. Steve, you want to go ahead?
I have field tested this double stud wall with plywood on the inside face. It passed in the field. However, there was a lawsuit over it because you could hear everything that was going on. And there's actually a paper from NRC that talks about the fact that when you put the plywood on the inside face of a double stud wall, the reduction in the distance is what drops all of the low frequency acoustic value. So people would talk about being able to hear a person open a drawer and take out a spoon. And that all comes from that. If you take out and do the test again with those two layers on the outside of there and put all the shear on the outside and there's nothing in the middle, that problem goes away. And the STC value jumps drastic or very largely.
Yeah. So Steve, in yours, you had a wall that just like this one on my screen, the STC 43. Was it a single layer of gyp on each side?
Single layer gyp board on each side, and actually there may have been 2 layers of gypsum board, and in fact on one side there was resilient channels also.
Oh, okay. Well, that
and-
will, if I click through here, like with resilient channel and 2 layers on one side, we're a 49. So if your wall just barely got through, like just barely met, then that is kind of in line with the data that I have here. If there was RC and maybe 2 layers on one side, but they could still hear everything, right?
Yes.
Yeah. Which goes back to that quote that I started with, right? That the code minimum is not enough, right? Yeah. Yeah, that's interesting. I'm curious if anybody else on here has other test data too that kind of maybe lines up with what Eric's saying. For especially the double shear interstitial layers with additional layers of gypsum board on the outside. I see Elzo's got a hand raised. Again, I think.
Yes.
Yeah, what's up, Elzo?
For Steve Pettyjohn on his double shear wall and his representation that you could hear a person opening a drawer and taking out a spoon, that can be cured with the PAC resilient channel backer and RCB. Now, that doesn't do anything for the voice, but it terminates the structure-borne path of sound transmission, airborne path of cabinets attached to a resilient channel wall.
Yeah, so the RCB, I'll just pull it up and slide it over here. This is the RCB. Let me find the good picture in here. We've got a nice somewhere. There we go. So it's a metal Z bracket with 2 of our boost isolators on it, and you put a 2x4, 2x6 stud mounted through the bracket through the isolators. And it's designed so that this offset of the Z bracket makes the face of the 2x coplanar with the face of the resilient channel. And then you install your gypsum board and you mount your cabinets to these backers. You can also do it in steel framing. You just form a box beam with a stud and a track, and then you would mount that to it. So you could use that to isolate cabinets and things like that to avoid that structural transmission of things like drawers opening, getting spoons out, and things like that. Any other questions or comments? If there's no other questions or comments, I mean, I'll hang out here for a little bit longer just in case anybody's got anything else. Yeah, this recording will go up as soon as possible. I can also like create a PDF of this that I can post sort of with the recording so that the slides are there and available with the data and things like that. If anybody's interested in that, or I can take it and put it in all the data is available in the database in our assembly selector. Yeah, I'm curious, you know, any other questions or any other sort of like shear wall configurations that folks have run into that are an issue or that you'd like to see data for. I see Ivan's got a question. What about drilling holes in the shear panels? We haven't tested that as far as I'm aware that I have like documented test data for. I think Elzo actually did do a test, but I think that we didn't, and I can't remember if it was like a gypsum board retrofit, which we do have some retrofit test data on steel studs, by the way. But I think the holes in the data that we have, I didn't have full documentation for or something like that. I'll have to go back and dig into those. In theory, it should work, but I think you need to drill quite a few holes. And the idea of drilling holes in the panel is so that you vent that cavity, right? So that you reduce that air stiffness coupling. And you basically make that small little air cavity back to closer to the full cavity, which then sort of lowers your mass air mass resonance. But in terms of, I'm not sure how that plays in like structurally, like from a structural standpoint to still get the shear performance that you need, how many holes can you drill, right? And then obviously from a labor standpoint, drilling a whole bunch of holes in there is, you know, we already have labor shortages and, you know, increasing labor costs and things. So having somebody drilling a whole bunch of holes, it, you know, probably doesn't really work on some big multifamily project, but maybe in select situations it could work. Yeah, there might be other folks on here too that have experience with that. I will have to go back and see if I have that data. I remember looking at it, but I can't remember what it told me.
Hey, Mike, check with Ben Schaefer. I don't know if he ever did some testing of that sort with holes.
Okay, I also said
Yeah.
he did it with existing layers of gypsum board. Yeah, and I remember seeing that. I think we didn't have full reports for it or something. I can't remember what the reason was why it's. I don't think I've put it in the database.
Yeah, we've tested with existing layer of gypsum board, just drilled holes in the gypsum board so that they didn't have to disassemble the wall and tote it out, and just add clips and purring channel insulation and another layer of gypsum board. And at the end of the day, the problems with the screaming kids in the nursery and the sound radiating into the main service area of a church was cured. So that was the test, screaming babies. And then we went to Wheel and did the same test with 7/16 OSB, and we drilled 4-inch holes in a staggered pattern in each stud cavity. And if I remember right, they were 16 inches on center. And
right.
yeah, it improved the result, but not as much as I anticipated. So I didn't pay for a formal report because I felt we needed a lot more research and something that was, you know, basically a step-by-step to find out what the magic point of free air movement, because it's an air stiffness coupling problem.
Right.
So as soon as we can get the holes close enough together to create free air movement, and if we look at an open web truss, we know that we can perf shear panels. The question is, what is enough perfs, and when do we make the shear panel no longer effective as a shear panel?
Yeah, right. That's the trick. For retrofit situations where you're not relying on that existing gypsum board for structure, maybe you've got more flexibility. But if that's your fire protective membrane, then you've got issues for fire also. And obviously you can't go drilling a bunch of holes in your fire protective membrane. So yeah, I'll have to dig back into that data. Maybe there's at least TL data that I can do a post on, and maybe a follow-up webinar.
All right. Any other questions? By the way, for all of you who have been on this presentation, I did post a link to register for the PAC International website. So if you don't already have a login access and you want to access some of the data that Mike's been describing today and all of our other data, go ahead and register there. We'll get you approved and you can get access to that data.
Yeah. Thanks, Steve. All right. Well, thanks everybody. I hope you all have a great day. We appreciate your time, and stay tuned for webinar for next month. Actually, next month we won't be doing a PAC specific webinar. I will be doing presenting along with Evelyn from Maxon. We'll be presenting on sound and fire design and floor and wall assemblies for INTS, the Institute of Noise Control Engineers. We'll do that, and I think that's sometime in April, towards the end of April. So watch for promotions going out for that, and yeah, and then we'll be back in May with another webinar for PAC.